I thank the organizers for giving me a chance to give this talk. It's a string phenomenology talk, which is a little bit different from the last couple of days. The work I'm going to talk about is done with student Sam Wong, and it's based on earlier work that I did with Yosuke Sumitomo, which I will review because it's that early result that leads to what I want to talk about today. So we know that the vacuum energy, dark energy, which I would consider to be a cosmological constant, has a value which is extremely small. The question is why the cosmological constant has a value so small compared with the Planck scale. And the way to answer that, the only way I think it's possible to answer that is the place in a model where you can calculate lambda. And string theory is a place where we can calculate lambda, and hopefully that's where we can find explanation or resolution to this problem. Maybe I should use this. One key observation that I'll use is by Busov-Puczynski, who observed that fluxes in string theories are quantized. They use this, for example, say there's J types of quantized four-form fluxes, and each one will contribute to the cosmological constant, where Q is dependent on the details of the compactification, and N are the integers because of quantized fluxes. And they give a distribution which is like this, and by choosing J big enough, since we have many, many possibilities, and they chose big J, the type of form for flux of order of 10 to 20, then they find that the spacing between next to each other lambdas is small enough such that some will have a lambda of the value that we observed. However, the question is, of course, that among all the flux choices, why nature picks such a very small positive lambda? And would like to propose, and I will explain to you the basic idea, is that we have to introduce interactions between these terms. And when you introduce interactions, then there's a statistical preference for very small lambda when the string dynamics is included. And I will illustrate this point with a particular model in this talk, although we have worked out a few models to see how this happened. And what we find is that when you have a statistical preferred lambda of the observed value, around the observed value, it's always accompanied by very light bosons, as light as 10 to the minus 33 electron volts and up. Now, at first sight, we think that this is a disaster, but maybe not. Recent cosmological studies suggest that bosons with mass scale of 10 to the minus 22 electron volts, which is very small, can play the role of dark matter, and it's very good for structure formation. It avoids the core problem that weakly interacting massive particles as dark matter have seems to appear in numerical simulations, numerical calculations. So this particular choice have been studied extensively. I'm here only quote some of the literatures, and it's been intensively studied. They form a Bose-Einstein condensation and seems to fit what expected from, for example, dwarf galaxies very well. So this means that taking the observed lambda and the mass square of this value, mass square over lambda is roughly 10 to the 22. Okay. So this is not that far compared with this when typical bosons will have mass of this type and heavier. So I'm going to go over this and argue that in such scenarios where cosmological constant is observed value, so these light bosons, at least order magnitude, within reach what we want for dark matter. I'm not going to talk about the cosmological issues of this. I just want to say that there's light bosons within reach of order magnitude that can play the role of dark matter of this type. Now, so the basic string model or typical we have is a set of moduli I call UI, and two-form fields C2B2, which have the flux, quantized flux. And in this case, what we have is we have a potential with the fluxes wrapping various cycles and the set of moduli. And since these are quantized, we can rewrite the potential of this form. Okay. So UI stands for a collection of moduli, which will couple together with the fluxes. And for each choice of fluxes, Nj can be order of 100, J can have 100 types, so I also think about of order 100. Okay? So as we sweep through Nj, they will take discrete values, and for each fixed sort of values, we can evaluate the metastable vacuum by solving the moduli values, and which is function of the Nj, and the cosmological constant of the minimums, all the minimums, locally stable minima, will be solved, and so it's a function only of the flux numbers. Okay? So the cosmological constant of the minimums function only of the flux numbers. Okay, now, since the flux can take a variety of values, then we can sort of find a probability distribution of these fluxes. Typically, we take some smooth and uniform, and I'll go over this, what we try to have in mind. And given this functional dependence on Nj, and given the probability distribution of each of the flux distribution, we can figure out what the probability distribution for lambda. Okay? And so once we know the probability distribution for lambda, we can see what value is preferred. Okay? So this is the exercise. Let me do a very simple model first. So let's consider this simple model with one field, play the role of a modulus, and then have some constant multiply x1 phi minus x2 phi squared plus c phi squared. So x1, x2, and c will play the role of flux values. Okay, they will take a discrete number of values. I didn't introduce a constant, which I'll come back in a moment. Okay. Now, for any fixed x1, x2, and c, it's easy to solve this. You can do it analytically. And then once you plug it in, you can calculate the lambda. And it's roughly of this form. And now we can say, well, let me take x1, x2, and c with some simple distribution, some uniform distribution, for the sake of discussion. Okay? And I calculate probability distribution for p of lambda. And we find it's peaked at 0. That means lambda at 0 is preferred. This can be done using exact formulas and numerically. Okay? So this peaking at 0 is quite generic. In fact, we see the following behavior. That means that the p lambda actually is very closely proportional to pz, which is function x1, x2, where the other coefficient c doesn't play much role here in terms of peaking. So now, we want to see how sensitive is P lambda or Pz depend on the individual flux distribution. Okay. So here's the first example. We take all the flux distribution x1. We also consider x1, x2, but we can also consider more. We consider xi for x, the pi for xi to be uniform between -1 to 1. And then we find that the Pz, z is x1, x2, is following the red line. And it peaks at 0 value and diverges at 0 value, actually logarithmic divergence. Now we can change the input probability distribution for the fluxes. Okay? See what happens. Well, we do a Gaussian, a normal distribution, and the divergent peaking at 0 is essentially the same. Okay? Difference is a little bit on the tail. We can take another distribution, sort of pick arbitrary distribution, and then the z, x1, x2, with this distribution for x1, x2 fed in, again, diverges at x equals 0 and peaks. Okay? We can choose something even different. So suppose we do following. We choose x1, x2, have a probability distribution that peaks and diverges at 1. Okay? In that case, when z equals x1, x2 equal to 1, then we are really weighing on the probability on this tail end. So we can look at the distribution for z now, which is function x1, x2. And surprisingly, it's smooth out here, and again, only peaks at 0. Okay? That's mostly because as long as the distribution for input discrete values is sort of smoothly around 0, pass through 0, this peaking behavior is there. We can even think about, well, maybe x1, x2 are correlated. In particular, suppose x1 equals x2. Then we find, again, the divergence of pz at z equals 0, where z equals x1 squared, because when x1 equals 2, is again there. Okay. So this is, the bottom line I want to say is the three things. The first, that the peaking behavior of p lambda is insensitive to the input probability distribution of the discrete spectra of fluxes, because usually that's a little bit hard to calculate. The second point I want to make, which is for the more realistic model, more general model, again is true, is that the constraint flux value for minimum is always there. That means that not all choices of possible fluxes will give you a minimum. A lot of time, there's no minimum solution. This is especially true when we have more moduli. And the third is that I didn't add a 0 to it. If I add 0 to it, then the peaking at 0 will disappear. Okay. And in fact, we can do the following example. We take the Busov-Puczynski example, which they essentially have terms which are not coupled to each other. And in this case, you can look at distribution, and typically there's no preference for 0. Okay, it's a sort of relatively smooth distribution, independent what input distribution you pick. Okay, so now let me go to a string theory, type 2 in particular, to be specific. We want to take a superpotential given by Witten, where there's free-form flux, free-form field string with here, and they will take discrete values in this particular compactification. And then we put this into a model which is motivated by orientifold, orbifolded model. So this is typical model that people have studied in the last 10, 15 years. And we just take the one model that people have studied and examine what happened to the solutions and distributions of the lambda. Okay. So in this case, the superpotential has Ci, Bi, Di are all essentially will be flux parameters, which will take discrete values, which will sweep through. Okay. The exercise is very similar to what I just talked about, except the model become somewhat more involved. And the basic idea is that we choose, let me show you the term. We have a non-perturbative term add to the superpotential. And the non-perturbative term will provide KKLT kind of uplift. So what we have is we solve for the supersymmetric vacuum in this case, and then uplift it by a non-perturbative term by a number of possibilities have been suggested. And this essentially is the way that we're going to solve this, or essentially that's the way that most people have been handling this problem. Okay. So again, for fixed Ci, Bi, Di, and A, we solve for the lambda. We find all the minimum, and then solve for lambda in terms of these flux values. And then, to simplify, we choose some real random variables with smooth distribution. And given this, and knowing lambda as a function of this, we can calculate the probability distribution of lambda. Okay. So this is what we did. And the bottom line is the following. P lambda is clearly very sharply peaked at 0, so it's difficult to plot it. It's not very illuminating. So what we did is we obtained the median value, which the 50% of the vector have a lambda below this value. We give the average value, and as a function of the number of complex structure moduli. So let me just stick to lambda is bigger than 0 for a moment. Okay. And we take the number of complex structure moduli to be larger than 5. where we can see asymptotic behavior. Then the median value for lambda goes like 10 to the minus number of complex structure moduli to the n prime to the 4. Okay? And the average value is actually stay more or less constant, change very little. And actually the average value in terms of what we have is very close to the strength scale that we put in. Okay. It's roughly gut scale. We also give you the lambda 10%, which means the 10% of vacuum has a cosmological constant value smaller than this lambda. Okay. And this scale is like minus 1.3 of the flux value. So notice that the average actually is a lot bigger, and the reason that it doesn't drop much is because there's a few, not many, but a few vacua have a cosmological constant that's pretty big, okay, of strength scale, and they dominate the average. However, if we take H21 to be of order of 100, then the observed lambda value more or less is within range. Okay? Similarly, I didn't show the negative CC. Very similar power up of vacua around lambda equals 0 happens also for negative CC, but somewhat different. Okay? So the preference is not only for positive, but preference is for anything close to 0. So typical manifold people have studied has a number of complex structure model of order 100. So when we choose something of order 100 is quite reasonable. We can also have more than one Kähler moduli. In fact, we study 1, 2. It doesn't make much difference in the overall property. Now, so suppose we have the observed value or close to the observed value. Now we look at the bosonic mass spectrum. Okay? All the moduli will pick up masses or semi-positive masses, mass square. And in this case, we can write down the mass matrix into some of all the fluxes. So Bi, Di are flux values supposed to be taken. And we find the following result. Okay? There are roughly the number of complex structure moduli minus 2 of the moduli, the real part at least, have a mass which is very small, very much compared to lambda. That's roughly 10 to the minus 33 eV. Then we have axions, equal number of axions, which is massless in this case. And of course, we can give them mass by some non-productive term, which one can put in. We also have masses which are heavy, but increases like a number of complex moduli square. So they are a few order of magnitude heavier than this. And then we have heavy ones, a pair of them, where the mass will increase as the complex structure moduli increases. Roughly, numerically, we get this result. Then, since we want H21 to be order 100, then so that lambda will come out of order magnitude right, then we find this masses is more or less of the range that are suitable for dark matter. So this is all order magnitude, and we can of course turn on other interactions in the superpotential and raise some of the masses here. Okay. This can always be done. So the bottom line is that when we have a cosmological constant, very small, not by fine-tuning, by a statistical preference, then a lot of light bosons always accompany the vacuum. And with the new insight in terms of dark matter, maybe this is a good feature and one should explore further. And we intend to do that. So the cartoon picture is roughly follows. Okay? We did inflation, that just we hear about. And after inflation wrote down and potential, and of course we are talking about many dimensions, many fields dimensions, so but we only plot one. And then you will hit there's no vacuum stable vacuum that will get trapped up here, and then it will just roll down to some of the very small Kotzebue constant. Most of the vacuum we find have very small Kotzebue constant, some positive, some negative. And then since we have to go through positive before we reach negative, it's likely to be trapped in one of the very small positive Kotzebue constant vacuum. So this is roughly the picture we have in mind. Now this is a little bit different from more generic picture. More generic picture is that typical vacuum will have rather large Kotzebue constant, but we can always fine-tune it. In almost any model, we can always fine-tune it to a small value. And this is by fine-tuning. And when that happens, we find typically these vacuum will have relative high masses. Okay. And then in this model, of course, you use some symmetry argument to argue why some of the fields are like axions can have very small masses. So the picture is sort of coming opposite direction. In the case that we have very light masses, and if we want a heavy boson, like a Higgs boson, we have to include more interactions. For example, we ignore the flux change, which really have some sort of equivalent potential, which have a very large mass. Hopefully that will handle why there's a mass of the scale of a Higgs boson. But generic, what we have is that opposite direction. We start from a vacuum with a lot of very light bosons, and then we turn on interactions which you have ignored because they're high mass scale, and then see how boson masses get lifted up, or higher mass bosons particles can appear, which is opposite to this picture where you have very high masses bosons or fields, and then you ask how symmetry or otherwise can give you light bosons. I think this opposite direction may give us insight into what's happening in actual situation. So let me summarize. So in this approach, we argue that most vacuum accumulate around lambda equals 0. Hardly any metastable vacuum exists at higher vacuum energies, which is not too surprising. If you have 100 moduli, a classically stable vacuum must have every single moduli with semi-positive mass squared. Okay. And usually, if you do randomly, that's not easy to happen. Now, so a lot of vacuum choice, a lot of flux choices will actually give you no solution. The second thing is that we find that, as the picture we just showed, whenever you have this vacuum which has very low masses, low vacuum energy, typically very high is very low as well. And that's why the masses are very small, because they're very shallow. And the very high, typically what we have is comparable to the Kotzebue constant, but tunneling, for example, is still very much suppressed, so we're safe. Require lambda to be observed value. Without fine-tuning, generic we give a lot of light bosons. And in fact, the next step is to how to find built-in interactions to raise boson masses. But to have something which is very light is relatively generic. The particular model we study, of course, is too simple. So instead of asking why the Higgs boson is so light, our question now is why the Higgs boson is so heavy, because in this case, to accommodate heavy bosons of 125 GeV is a challenge. Okay. Thank you.
Yeah, it's interesting. Your model is in some tension with Busa-Lachinski and all the subsequent work about the subject. And if one can sort of get distributions of that, you get lambda equals 0, then you need to ask what is special about lambda equals 0 that makes up that value for the peak. And in your examples and the other work you described, it seems that what's special is that you leave out the at-0 term in the original potential of the air vacuum and the quantum corrections. And that's not expected to be the case in strength of the quantum corrections, so the supersymmetry index.
So Yeah, so in the phi cube model we left out the constant. And what it means is the constant is a sector which is decoupled from the phi cube, for the phi field in that case. And in generically case, if there's a sector which decoupled from the other sectors, then the preference for lambda equals 0 will essentially disappear. But the way we argue is that in string theory, everything is coupled to everything else. There's no sector that's decoupled. And that's a key to the reason that we can get this peaking behavior. And so we examine a few models in string type 2b, and it's all coupled, and that's the key.
No,
if you have a sector which is
the
uncoupled.
energy does couple to gravity. And,
Yes, all closed ring sector.
There is a constant term in imaginary potential. There is not a priority argument. If there were a priority argument excluded, then we would have a much simpler solution to the cosmological constant problem, which would be simply to take the fluxes to be 0. And that would be a preferred thing.
Flux goes 0 is included in our discussion.
And it's much simpler than the others.
But what I want to say is that sometimes when you have flux equals 0, essentially there's no minimum solution. So it's the interaction is what drives the dynamics in this case. Well, I should comment that in your work you have done also you have looked at sort of random distribution for W and then for DW and DDW. And what we find is that once you have the interaction and look for minimum, they are coupled. So they're correlated. So that's where the difference is. We can discuss.
Yeah, hi. I'm certainly confused about all these light species in terms of the cosmology. I mean, shouldn't we see them? I mean, if there's a huge number of species that are essentially relativistic, shouldn't that change the history of the universe in a way that we would see it? It would be pretty constrained, right?
Yeah, this is a cosmological issue. So what people have done is that if you produce very light bosons, like 10 to the minus 22 eV, so what happened is that the expansion universe will probably slow it down, and then they form a boson-Einstein condensation. And it's in the context of boson-Einstein condensation when we look at structural formations, like wall banks. So they form, the condensate is very important.
I just want to say there's a more standard answer to the last question, which is that, after all, gravitons aren't important in the cosmic evolution because it's presumed that they weren't in thermal equilibrium. If you assumed that gravitons were in thermal equilibrium, they would substantially affect things like nucleosynthesis. And for whatever reason, the gravitons weren't in thermal equilibrium, one would want to say that all these other light scalars weren't.
The sense the thing again.